So I think this, if I'm not mistaken, and I very well could be, but I think this is going to be the last part of our heat exchange unit that we're going to work on before we move into the end of the project and the test. And we're going to talk about contraction and expansion. Now, I know that if we look at our anchor charts, I know that I write it tiny, but I always have the learning target on there. Like, we need to understand about the three ways that heat can move between objects. And the reason why is the bottom of that says, in order to understand how that changes an object, when heat is taken away from or given to an object, that object is going to go through changes. And some of those changes are contraction and expansion. We'll talk about some of that today. When we add heat to a substance, the molecules inside of that substance start to move. Everybody remember the video of the guy holding the bar over the flame? And it showed that the molecules, the atoms, started to move further and further and faster. We can't really see it because we're not that small, but as we add heat to things, most things are going to expand. That means they're going to get bigger as we add heat to them. If you look in the background here, you see there's this giant gap here. That giant gap is probably on a bridge that's built somewhere, because in the summertime, as that bridge gains heat from the sun, because we all know that asphalt can get really hot, it's going to expand, and because those spaces are far apart, they can actually be pushed together a little bit. In the wintertime, which looks like this is probably what that is, things are going to contract and get a little bit smaller, so that bridge has a space to move instead of buckling if you just built it without any thing in there for it to move backwards and forwards. When we think about thermometers, we've all went outside and looked at the thermometer before, yes? Like, we look at the red thermometer and we say, oh, the temperature is 84 degrees, or oh, today it's like 60 degrees outside. When we look at that thermometer, the reason why that red goes up and down is because as it gets hotter, the molecules inside of that start to speed up and they get further and further apart, thus pushing that liquid that's inside of there higher and higher, making, as it gets cooler, like it does at nights now, the molecules lose that heat energy and they actually get a little bit closer together and they contract and they go down. And that's why you see the rising and lowering of that red line on a thermometer. I drew that on my anchor chart. You can use that in your project today if you want to. I know some students have done other things. They've talked about railroad tracks and bridges, which is fine as well. Any of those that make sense to you are going to be fine. So let's look at that thermometer. Here is what it would look like, Josie, if we could actually kind of see like the particles inside of that. Again, as there is less heat, those molecules are going to get closer together. Therefore, the liquid is going to contract. It's the same amount of liquid in there, whether it's hot or cold. I know it seems like there's more liquid when it's way up here, but there's not some magical fairy that fills it up when it's hot and takes it away when it's cold. It stays inside of that tube the whole time. But the reason why it moves up when there's more heat is because those molecules are spread out further apart. Does that picture kind of make a little bit more sense now? I know that we typically don't think about how a thermometer works. We just know that I want to know how hot or cold it is. I look at the thermometer, moving on. This is how it works. This is how it works, which is kind of unique in the way that those work. Here's another picture, a little bit closer up picture. You'll see this. I see this a lot on the bridges when I go to Wilmington. Like when I'm walking around in Wilmington, I see these types of gaps in bridges. Yes, sometimes those are there because the bridge is a drawbridge and opens and closes. That's not what that's for. That's going to be so that the bridge can expand when it gets hot. Those are going to push really, really close and contract in the winter and probably pull about that far apart. Now, are they going to build the bridge where there can be like a giant, like 8-foot gap in the winter? Well, no, because the engineers know better than that. They understand the materials that they're using. They understand how far apart they're going to expand, and how they're going to contract, and then how close they'll get when they expand, and they build it accordingly. That's why it's so important for people that go into engineering to understand heat exchange as they're building these bridges, so that in the summer times and in the winter times we don't have collapse and failure. This is what it looks like with train tracks. If you just lay down giant, long, straight train rails, they're going to overheat and they're going to buckle like this. Now, this one is not terrible. This one right here, your train could not stay on that track. I don't care. I mean, I can't imagine. Even if the train drove super slow. This one, it just moved the track this way, which is a little safer. It probably wouldn't make it on here. This one, I think if you went slow enough, but if your train was moving at a high rate of speed, you can't hit curves like this that fast. It'll come off the rails and cause a massive accident, which wouldn't be good. So, I mean, we can't do this, unfortunately, but if we were able to walk up to the train tracks up here and walk along those, we would find that there are places that there are spaces, gaps in the train tracks so that those rails can expand and contract. Obviously, now that we've advanced with technology, they're able to put sensors on the train tracks that let us know when these types of things happen, and they can go out and get those fixed before trains go across them. Again, adding heat and expansion. Now, again, we could write all the words on here down. This is like a fancy way of saying all this. Thermal expansion can become a problem for trains and bridges because it will cause the rails to buckle, to bend like that. Again, there's monitors now. Sometimes they actually even paint the insides of the rails white. Why would you want to paint something white to avoid the buckling of that, Knox? Darker colors attract heat, lighter colors reflect it, white being the best one to reflect that heat. You are correct. So let's take a look at the notes that we took on expansion. If I can I get to them? So this is the same thing that's on the anchor chart over there. Adding heat to objects can cause expansion. Jonathan, expansion means when things get bigger, like they grow. We'll watch a video about this here in a few moments. Bridges and railroad tracks need spaces because as things heat up, the molecules move faster and farther apart, causing expansion. So I'm going to give you some time to jot that down in your notebooks. You will be asked to repeat some of this information in the project that we'll talk about at the end of class today. All right, so Colton, we know that when we add heat to things, they expand, they get bigger. So there has to be a converse to that, an opposite to that, and there is a converse to that. Not again, there's always exceptions to the rule, and trust me, water is going to be a big exception here in a minute. Most things, when they are cooled, contract, meaning they get smaller. Most things, water does not get smaller when it gets cooled enough. So that same train track, if we measured it during the summer, let's say it was 16 meters. If we measured it during the winter, it might be 15 3/4 of a meter. No, but Mr. Bones is the exact same piece of metal. Did somebody shave some of it off? No, it expands and contracts. And again, when we watch the video in here in just a minute, and we all laugh because it's funny, we'll see metal expanding and contracting in an experiment that people do. But it's interesting to see how things, when they cool off, they contract. So let's find the notes that we did on that. Maybe or maybe not. There it is. When things are cooled, the molecules get closer together and the object contracts. It gets smaller. Again, this is why there are those spaces on the train tracks and again, same thing for those spaces on the bridges. They are there not just for expansion, Knox, they're there for contraction as well. Like, to be an engineer, you have to understand what material you're using. You have to do the experiments, or at least read the experiments on how they contract and expand before you start building something major Otherwise, you could really cause something that's pretty bad. We've talked about how thermometers work. You might notice that I actually put this picture in the background and my explanation on the anchor chart today while we're doing the project. If you need to go over there and look at that and write that down in your notebook or use it to put in your project, you're welcome to do that. I'll give you the class code. You can come back into this and look at this page all you need to. That'll be fine. Yes, ma'am. If it gets hot, it's going to some, yes, unless it's made out of a material that is able to resist that, because a lot of the things on the spaceship is going to be insulation. So it's not going to have as much heat move through it, so it's going to resist that. All right, this device only. Someone will pause the video. We'll watch this when I get done with the video. I'm going to make sure I get all the notes done before I finish that up. Now, water's very weird, all right? Thank goodness. You'll understand when we watch the video. It's very good, Ava, like very good that water does not act like most materials. If water contracted when it freezes instead of expanding, which is really weird, it expands when it's heated and expands when it's frozen. If it didn't do that, in the wintertime, fish would die. I'll show you in the video why. Fish would not be able to make it if that's what happened. But again, water is weird. It expands when it's heated and it expands when it is frozen. Think about in the wintertime. Why do we have to winterize our homes? Why do we have to put insulation around the pipes? If the water freezes, the pipe would bust. That doesn't make sense if the water gets smaller, right? Water actually gets bigger when it turns into ice. It expands. It's all because of the way the molecules are and the attraction that they have between each other and the negative and positive values that the atoms have. But that's stuff for like 8th grade. Again, water expands when it's cooled. You need to know that. That's extremely important. They love to put that on the test. You do not want to put your favorite Return of the Jedi glass with water in it and Darth Vader action figure in the freezer. Because if you do that, it will expand and crack the Darth Vader glass. I know. Am I over it? No, I'm not over it. But I learned the hard way. Then I learned to just put the Darth Vader action figure in plastic trays and let that freeze, and then have frozen action figures when I was playing with them, instead of losing your favorite Burger King glass from when you were little. But yeah, you can't put your bottle of water in the freezer. You cannot put a Coke in the freezer. As good as those Cokes taste when they get slushy, if you do that, you're running the risk of the water in there freezing and expanding and breaking the bottle that it's in, especially if it's glass. It will make an absolute mess. Later on, Google people that have left 12 packs of soda in their cars on a winter night. It's a wreck because the cans expand and explode, and then all that carbonation and soda goes everywhere, and they come out to an absolute mess in the mornings. You cannot let things that are enclosed with liquids in them that have mostly water do that, because they'll expand and freeze, especially the pipes in your house. Not fun, not cool to deal with on a 15-degree morning when the pipe bursts and you have to crawl into your house before you come to school. Not a lot of fun at all. Mr. Bullens, why do you have mud all over you? Be quiet. We're reading silently in class today, guys, because Mr. Bullens is freezing and angry. True story. So again, we'll talk about that as we move through. Again, water expands as it freezes. Liquid water expands, it says, by about 9%. So it gets a little bit bigger, and it takes up more space. How do I know that it expands and it's less dense than water? Because ice cubes float. If ice cubes were more dense, they would sink in water, and they do not. They float. So that's one of the ways that we know that, and one of the ways that we can look at that. The rest of this stuff in the slides is going to be videos. So for the folks watching at home, have to what? Smash the like button and subscribe, and click the bell for notifications. Absolutely. All right. Peace out to the people at home.